On the 1st of July 2025, a telescope in Chile spotted something unusual. The NASA-funded Atlas Observatory in Rio Hurtado was doing its routine survey of the night sky when it caught a faint object moving through the constellations Serpens Cauda and Sagittarius at magnitude 18. It was dim, but its motion immediately stood out to the automated systems. The object received a temporary label, A11.3Z, and was posted to the Near-Earth Object Confirmation page. This is essentially a waiting room for newly spotted objects that need more observations before astronomers can say what they actually are. The initial detection was just the beginning. What followed was a global effort to track this visitor. Professional observatories turned their telescopes toward it. Amateur astronomers joined in from backyards and remote observatories around the world. Each new observation helped refine the calculated path, and the more data that came in, the clearer the picture became. The trajectory was hyperbolic. That single word carried enormous weight in orbital mechanics. A hyperbolic path means the object is moving too fast to ever be captured by the sun's gravity. It came from somewhere else, and it is leaving forever. This was not a comet born in our solar system. This was a true interstellar wanderer, just passing through. The confirmation marked only the third time humanity has observed such an object. The first was Oumuamua in 2017, then Borisov in 2019, and now this. Each one offers a fleeting glimpse into planetary systems far beyond our own, carrying clues about corners of the galaxy we may never reach any other way. The name 3 Atlas tells a story in itself, and understanding it helps place this object in a remarkable historical moment for astronomy. That small prefix 3 carries a lot of meaning. The letter I stands for interstellar, marking this as something from beyond our solar system. The number 3 tells us something even more striking. This is only the third confirmed interstellar object ever observed by humans. Think about that for a moment. In all of human history, in all the centuries we have been looking up at the night sky, we have confirmed exactly 3 visitors from other star systems. The first was Oumuamua, spotted in 2017. It was strange and elongated, and it sparked endless debate about what it might be. Then came 2I Borisov in 2019, which was clearly a comet from another part of the galaxy. Now we have 3 Atlas, and each discovery adds to a very short but growing list. The Atlas, part of the name, comes from the Discovery program, the Asteroid Terrestrial Impact Last Alert System, which operates telescopes designed to scan the sky for near-Earth objects. It is fitting that a system built to watch for threats from within our solar system ended up finding something that came from far beyond it. There is also an alternative designation for this object, C 2025 N1, which follows the traditional comet naming system. The C indicates a non-periodic comet, meaning it will not return in any predictable cycle. The 2025 marks the year of discovery, and N1 is a code indicating it was the first comet discovered in the first half of July of that year. Both names refer to the same object, but the 3 designation tells us something the other cannot. It reminds us that this is a visitor from another star passing through our neighborhood, briefly before continuing its journey through the galaxy. So what exactly is this object? The observations have painted a remarkably clear picture. 3 Atlas is an active comet, which means it has a solid icy nucleus at its core, surrounded by a glowing coma of gas and dust escaping into space. The Hubble Space Telescope turned its powerful eye toward the visitor and measured the nucleus. The estimates place it somewhere between less than 1 kilometer across to perhaps as much as 3.5 miles. That is a fairly typical size for a comet. But what lies inside turned out to be far more interesting. The James Webb Space Telescope trained its infrared instruments on 3 Atlas and found something unexpected. This interstellar traveler is unusually rich in carbon dioxide. That finding immediately caught the attention of astronomers because the abundance of this particular gas tells us something about where and how this comet formed. Alongside that carbon dioxide, Webb detected ice water vapor, carbon monoxide, and a compound called carbonyl sulfide. That last one is particularly intriguing to scientists because it is a molecule that can be produced through various chemical processes, some of which might hint at the conditions in the original system where this comet was born. Meanwhile, the European Southern Observatory's very large telescope in Chile made its own contribution to this portrait. It detected cyanide gas and atomic nickel vapor streaming from the comet. Here is the fascinating part. The concentrations of these gases look remarkably similar to what we see in comets native to our own solar system, despite traveling who knows how far across the galaxy. Despite originating around some distant star, we may never identify this object. Carries chemical fingerprints that would not look out of place among our own cosmic neighbors. Speed defines this comet's story. When it was first detected, 3 Atlas was already racing through space at 137,000 miles per hour. But that was just the beginning. As it fell deeper into the sun's gravitational embrace, it accelerated. By the time it reached its closest point to the sun, it had climbed to 153,000 miles per hour. This makes it the fastest object ever recorded passing through our solar system. The shape of its trajectory tells us something crucial. Its orbit is hyperbolic. That word has a simple meaning in this context. The path is open, not closed, unlike planets that circle the sun endlessly, or comets that return every few decades. 3 Atlas is on a one-way journey. The sun's gravity bends its path, but will never capture it. The comet will eventually exit our solar system entirely and continue drifting through interstellar space. When it leaves, it will be traveling at the same speed it entered. Its journey through our cosmic neighborhood brought it past several key points. On October 3, 2025, it made its closest approach to Mars, passing at a distance of about 29 million kilometers. Less than a month later, on October 29, it reached perihelion, coming within 203 million kilometers of the Sun. Then, on December 19, it made its closest pass by Earth at roughly 270 million kilometers away. That is about 1.5 times the distance between Earth and the Sun. Throughout this entire passage, the comet posed absolutely no threat to any planet. During its closest approach to Earth, it was actually on the far side of the Sun, keeping its distance in every possible way. Once the discovery was confirmed, the astronomical community swung into action. This was only the third interstellar object ever seen, and researchers worldwide were determined to learn as much as possible before it sped away forever. ESA's Planetary Defense Office coordinated tracking efforts using a network of telescopes spread across 3 continents. Observatories in Hawaii, Chile, and Australia worked in concert, their positions allowing for continuous monitoring as Earth rotated beneath the sky. This global approach ensured the comet was being watched whenever it was dark somewhere on the planet. The tracking got a significant boost from an unexpected source in early October. Data from ESA's ExoMars Trace Gas Orbiter, which normally studies the Martian atmosphere, was used to refine predictions of exactly where the comet would appear. Those observations improved the accuracy of location predictions by a factor of 10. Having such precise coordinates meant astronomers could point their instruments with confidence, wasting no time searching for a faint moving target. But researchers also looked backward in time. They began searching through archived telescope images, hoping to spot the comet in data collected before anyone knew it existed. This process, called precovery, combines the words pre and recovery. Astronomers found what they were looking for. The earliest detection came from images dated May 7, 2025, a full 55 days before the official discovery. Finding these earlier appearances helped scientists plot the comet's trajectory with remarkable precision, stretching the known path from just a few weeks to nearly 9 months. There was one significant gap in the observations, though. For a couple of months during summer and autumn of 2025, 3 Atlas passed behind the Sun as seen from Earth. The glare made observation impossible. Astronomers had to wait patiently until early November, when the comet reappeared in morning skies, offering another window for continued study as it began its long journey back into interstellar space. What makes 3 Atlas so valuable to scientists is not just that it comes from somewhere else. It is what this visitor carries with it. Every planet, every moon, every asteroid in our solar system shares a common birth. They all formed from the same cloud of gas and dust billions of years ago. But 3 Atlas is a true outsider born around a different star entirely. Astronomers believe the comet originated from one of 2 regions in our galaxy called the thin disk or the thick disk. These are not actual disks you can see, but rather populations of stars and objects that orbit the Milky Way at different distances and speeds. If 3 Atlas came from the thin disk, it would be similar in age to objects in our own solar system. But if it originated from the thick disk, the story becomes far more extraordinary. Thick disk objects are ancient, and in that case, this comet could be at least 7 billion years old. That would make it older than our Sun itself, a wandering relic from an earlier era of galactic history. This is precisely why interstellar objects matter so much to science. They are like time capsules from distant worlds we can never visit. When 3 Atlas releases gas and dust as it warms near the Sun, it is revealing the chemistry of another planetary system. The elements and compounds embedded in its ice, formed under conditions we can only guess at. Each observation tells us something about how planets form and evolve elsewhere in the galaxy. We are essentially reading a letter sent from billions of miles away, written in a language we are still learning to translate.